And Mark, are you with us?
Yes, I'm with you. I'm just trying to get to the beginning of the presentation right now. Does everyone see that? You should see Falcon Space.
We see it.
I could see it. Science for humanity.
Okay, so this is the company that I started. It's called Falcon Space because my last name is Sokol, which means falcon in Russian. And the goal of Falcon Space is advancing anti-gravity technology. And I'm of the belief, and so is my team, that whatever you do experiment-wise, whether it's positive or negative, so long as you promulgate those results and get them out to the public, you will be advancing anti-gravity technology. And by anti-gravity, we're talking about how that little flying saucer in the corner works right next to the Falcon. So we're trying to figure out how those craft work. We're just assuming that they're real and trying to make them happen. Now, I hope I'm going to go in the right direction. 1 second. Okay, now I can do that. No, wrong way. Okay, so this is the team. There are other members that didn't make it to the lab yet. We have Jeremiah on the right. That's me in the center, and Jeremy on the left. I know it's a little confusing. We've got Jeremy and Jeremiah. Jeremy is pretty much our media man, and he's also like human resources. He's connected a lot of the dots with the people, and he also
connected a lot of the people, you know, with each other. Like we have Jeremy to thank for ours meeting up.
Exactly. And he also connected all the people together because he's really been at this the longest, been diving through the mud of anti-gravity, misinformation, because there's so much freaking misinformation out there. It's really crazy to dive through. So again, like I was trying to say with Paul's presentation before, which is beautiful, there's going to be a lot of disinformation. There's going to be a lot of wrong stuff. We just need to be not afraid of making mistakes, because if you're afraid of making mistakes, you're never going to try. Here we are inside of the Faraday cage where we run many of the experiments. It all depends on levels of radiation that are coming out. The Faraday cage is double shielded. The center, it's all made out of aluminum, and it goes down to an 8-foot rod. And then there's a second layer on the outside. So it's a bilayer Faraday cage. And the outer layer is attached to a separate grounding rod. And this assists with certain types of radiation to protect us and to also protect the experiment from any outside influence. Although I do understand there's many experiments that can't go on inside of a Faraday cage. It all depends on the amount of EM radiation that's coming out that we would have to protect ourselves from. Okay, moving on. This is the front control room of the lab. There's different types of equipment that are set up over there. You can see there's holes in the wall that allows you to connect into the Faraday cage. This is all set up in the back of a hybrid battery shop, which is my bread and butter. It's called Falcon Hybrid. Guess where we got the name from. So yeah, that's what I do for a living, basically refurbishing hybrid batteries. In the back, we're doing the anti-gravity work. Okay, and this is our second lab space, which is a little farther back in the shop. This is where I am right now. This is where we do most of the assembly and some of the smaller experiments, or the experiments that don't need a Faraday cage for, we run in this room. Okay, so why are we doing this? Why isn't MIT doing this? Why isn't CERN doing this? Well, it comes down to the Mansfield Amendment. The Mansfield Amendment was passed in 1969 as part of the fiscal year 1970 Military Authorization Act, prohibiting military funding of research that lacked a direct or apparatus relation or parent relationship to specific military function, meaning that if your theory went against general relativity and it wasn't within the doctrine of the cult of science, and I'm saying that sincerely, I think parts of science are a cult because they're all just following this one direction. You got to be able to go onto the fringes if you want to push the edge. So basically, anything like anti-gravity was rejected in terms of getting government funding, and this is the reason why. Prior to this, we had Project Blue Book and many other projects that looked into anti-gravity and flying saucers and all that stuff. And it wasn't until Senator Reid came forward with the ATIP program, he managed to stick that in there, that real money went back into investigating UFOs, or now what they call UAPs. So this is why we are doing what we're doing. And what are we doing? So we're trying to figure out anti-gravity. What is anti-gravity? Well, if you search online, there's two things that you'll most probably come across. The first thing is warp drive. Okay, and this is based on Einstein's general relativity theory, that gravity is a warp in space-time caused by matter. I disagree with that, mainly because I don't find that there's any evidence that space-time is warped. It may be a density issue of space-time that causes light to curve around large objects, but I don't think it's a warp in space. Therefore, it will be theoretically possible to according to that theory, it would be theoretically possible to create a warp drive in front of the craft using negative matter, and the craft would surf on a continuous wave of warped space. Well, how much negative matter? Alcubierre first talked about, I think, Jupiter size, and then they knocked it down to the size of like a golf cart, but it doesn't matter because standard model of particle physics does not include negative matter. We have antimatter. That's not negative matter. So yeah, this thing's not going to work. The next thing is, and this you'll find everywhere. This is, when talking to the average layman, this is the first thing they bring up is Bob Lazar's sport model. Well, just to give you the rundown, he claimed to have worked on reverse engineering alien spacecraft at ACE-4 near Area 51. Propulsion is achieved by amplifying the gravity wave of element 115, using that to direct the craft. Energy is produced by hitting element 115 with a proton, making it element 116, which is antimatter, which then interacts with the gas that turns it into pure heat energy, which then converts to electrical energy using 100% efficient thermoelectric converter. This is all BS. The explanation is BS. I'm not certain that Bob Lazar never saw a alien spacecraft at S4 near Area 51. That is a possibility. I think it's actually probable that he saw that, given what we've learned about Area 51 since then. But the explanation that he was fed doesn't make any sense, because element 115 is not stable. And most importantly, to all you physicists out there, element 116 is not antimatter. You can't turn matter into antimatter just by adding, a neutron or a proton. It doesn't work like that. Also, his story is widely available online and shows up prominently in search results. And what we talked about before with disinformation. So this is most likely a piece of disinformation because they want it shared. That's why we give it a big X. But Bob Lazar did say something, and this was his own intuition. So this wasn't what he was fed about the craft. And we're going to listen to that right now. So I can push play.
Also, that's almost a byproduct of the reactor. The reactor also sets up a gravitational wave from the 115 being bombarded. This gravitational wave is present at the top of the reactor and is essentially guided in the same way microwaves are guided through tuned tubes. And this goes to their amplifying cavities and through the projectors that are in the bottom of the craft.
Okay, so we talked about microwaves being guided through tuned tubes. Okay, that's kind of interesting because here is an experiment, paper written by Frederic Alzofon that talks about microwaves being used in a device or in a craft that will basically make the craft weightless through a process called pulsed dynamic nuclear orientation. And let's dive into his paper. This was published at Colorado Springs, Colorado in 1981. It was a peer-reviewed paper. He actually applied for a patent on this technology, which was rejected, which is why he felt it was okay for him to publish the paper, because there's already a patent that was patent pending at the time. So he thought it was kosher to go ahead with this. I found this not through general searching. I found it through a comment that was left on one of my videos with Jeremy Reese. And Jeremy never heard of it either. So that got me excited. Okay, so let's dive into it. Abstract. I'm just going to read a couple things that I thought were really put this into perspective. It's a method of decreasing or increasing the gravitational force on a vehicle using presently known technology. Suggested various ways of utilizing this effect on a vehicle propulsion are described in this paper. A unified field theory is then detailed, which provides a more formal foundation for the gravitational field model first introduced. In distinction to the general theory of relativity, it features physical processes which generate the gravitational field, meaning that instead of it being a side product of there being matter, that it's warping space-time, he's saying that the matter itself is emanating some sort of field which changes the density of space-time. It changes the amount of interactions, the amount of field effects that are going on because the matter itself has these field effects. Another important point is inertial mass, gravitational mass, and the electromagnetic field are exhibited as different states of the same field. And this also goes into, the metaphysical and Kabbalah, where they talk about the Or Ein Sof, or the infinite power of the universe, that everything is really one. It's 1 and 0 at the same time, or it's completely infinite. So it really brings together a unified field theory to explain everything. I'm not so certain that the math is correct. I'm not so certain that anything is correct, but the most exciting thing is that he actually has an experiment that we can try, which involves microwaves, and it makes sense. Okay, so the introduction here, the most evident property of the gravitational force is that it appears in the presence of matter measured by inertial mass. There's an equivalency.
No. Just throw them in that box.
Okay. There's an equivalency connection between inertial mass and gravitational mass. So we'll get into that a little later. It's also remarkable that no matter what the state of matter is, temperature, voltage, it doesn't matter. The same law, Newton's law of gravitational force, remains an accurate representation of the force between the two masses. And that this is dependent solely on the masses and the separation of the two bodies. And it, of course, follows the inverse square law that the farther you go out, it drops by a factor of 2. In applying the model, it is necessary to show how subatomic particles, whatever their nature and frequency of occurrence, can all give rise to the same force field. So we need to find something that is fundamental to the subatomic particles to understand what's really going on here. So we're really trying to simplify things a lot and just get down to the basics. Once having described the model of the process which arise to the force of gravitation, a procedure can be proposed which the force may be altered, i.e. weakened or strengthened. So we really need to investigate the problem before we can come to a solution. So it's not really how do we create anti-gravity, it's why isn't there anti-gravity in the first place? And I alluded to that in a couple of questions in the chat. It's, not how can it fly at Mach 22, and not burn up. It's why does the rockets, or why does the Apollo craft that are coming into Earth's atmosphere, why do they burn up in the first place? We know that's friction, but that's interaction between atoms. So we're going to get all into that a little later. Here we depart from Einstein's geometrical formula of the gravitational field, which does not indicate any physical process leading to the origin of the field. So we're going to separate ourselves from Einstein, where he thinks space is curved, and we're going more in the direction of, no, these are direct interactions between matter. So there's the kinematic model for the gravitational force, and basically it's I think I may have skipped a page here. Oh, okay, I'm pushing the wrong direction, that's why. Okay, so basically in the presence of another particle, and with the above mentioned localizability of both particles, the mass density distribution of the first particle is altered since the fields of both particles overlapped and share some of their masses with one another. Basically what he's saying is that all matter has a field that extends to the ends of the universe. Most of it is found in its center, right where it is in that almost indistinguishable tiny spot. But there is an energy field that goes out to the edges of the universe, meaning that literally every particle is infinite in its own right. So therefore, there's an alteration in the mass energy distribution between two particles, because now they all technically occupy the same space. Therefore, Le Chatelier's principle, according to Le Chatelier's principle, the two objects would have to come together in order to compress and become one. Similar to the way water tension works, like in outer space, if you have a water bubble, it'll coalesce around a circle. And this is something I showed in my previous presentation. Okay, so how do we get a anti-gravity device? What is the experiment? Bottom line. So implementation of an anti-gravity device, it works like this. The summary of the experiment: you're using pulsed dynamic nuclear orientation is applied to a paramagnetic atoms in a constant magnetic field. This is essentially what you do in NMR or EPR. And then you're pulsing it with a microwave beam. The microwave beam, you're hitting it at the Larmor precession of the valence electrons, and you're pulsing it. This adds energy to the valence electrons, and when you remove that energy, or you remove that RF, they're now in a high energy state, and they need to transfer that energy somewhere, so they transfer it through hyperfine coupling to the core of the atom. Now, what's happening in the core of the atom is the subatomic particles are slowly getting oriented along with the valence electron, because magnetism is nothing more than electron orientation, electron spin orientation. So if you have a strong magnetic field, you're orienting the electrons based on the strength of the magnetic field. And the stronger the magnetic field, the more they're oriented toward that plane. And therefore, their Larmor precession, which is the spin of the axes of the electrons, starts to speed up the stronger you have the magnetic field. It goes at around 28.025 gigahertz per Tesla, meaning that at 1 Tesla, you'd have to hit it at around 28.025 gigahertz, which is pretty high frequencies. 1 Tesla is a pretty strong field. Also, you need very high homogeny in the field, because magnetic fields are pretty hard to make them. It's pretty hard to make them perfectly laminar, so that the strength is the same throughout. Because if you're off by a little bit, then your frequency would have to be, in a pretty large range in order to theoretically run this experiment. He also talks about different materials that you would use. So he suggests using a very pure isotope of aluminum. That's because aluminum has the property of retention of the dynamic nuclear orientation for longer than most metals. Also mentions you can use there's aluminum, and also magnesium can also be used. It also includes iron, because the iron will connect with the magnetic field better than the aluminum, because it has more valence electrons. And by orienting the core of the iron, you can then use that to orient the core of the aluminum, which is in the same matrix. And because dynamic nuclear orientation is contagious, or it's like sort of like a magnetic effect, since you're orienting the electrons for a magnetic effect, or magnetism is electron spin orientation. What he's proposing is that anti-gravity is nuclear or subnuclear or subquantum orientations. If you could control the spins of these subatomic particles, you will have an anti-gravity effect. His reasoning for it is that the gravitational field emanates from the subatomic particles. So if it really is a direct connection between matter, that is sucking us together. And it's literally just, 1/100 billionth of the strength of what's in the core of the atom. So literally gravity is a form of electromagnetism. If that is true, then the field coming out of Earth is probably very incoherent, because second law of thermodynamics states that everything goes from a state of entropy to a state of order to a state of entropy. So in the core of an atom, you expect tons of entropy going on there, with the spins going in all random directions, right? So that means the field of Earth is all random, and every once in a while it matches up with the atom in in the meteorite or whatever's falling toward Earth, and then they pull on each other. So it's really a feature of how disorganized the atoms are, or the subatomic particles are, to allow these connections to happen. And in a macro scale, you don't really see much of this, because we've never really done much with orienting the subatomic particles in an atom. In fact, a lot of the equipment that I'm using to run this experiment is stuff that is no longer available, which is another point that something interesting is going on here. And I think I pushed in the wrong direction. Okay, yeah, made that mistake again. So the interaction of the disordered matter energy creation annihilation field, meaning the gravity field generated by the Earth, and the oriented or the ordered aluminum nuclei and its inclusions of iron, lead to a disordering of the aluminum nuclei and the inclusions orientation. So the Earth's gravitic field, which is completely disoriented, is trying to interact with the ordered field lines of the craft, but it can't do that because it would have to do work on it. And by doing work, it essentially cools down the gravitic field of the Earth. Well, I mentioned earlier, there's an equivalency principle between inertial mass and gravitic mass. We've never seen them to be any different. And there's actually an equivalency theory on top of this that I thought up and wanted to add to it. So what if the source of the inertial mass in everyday objects and in everything in the world comes from the subatomic particles also? So think of subatomic particles as a whole bunch of gyroscopes, and they're all spinning at the speed of light. They're basically light that is spun in on itself. That's what a subatomic particle is, or that's how he thinks of it. So that would make them into gyroscopes. So if they're all spinning and oriented in different directions, and they have different precessions and all that, and there is a connection between complex rotational speeds, or complex angular momentum, and linear momentum, which Mike Gamble, and last week he actually brought that up and showed that they were actually working on that, and it produces a force. So there is a connection between complex gyroscopic spins and linear motion. So if you had a whole bunch of complex gyroscopic spins of subatomic particles made out of light, and they're all spinning in different directions, and you move that object in a linear fashion, aka you threw a baseball, or you drove a car, then you are literally changing the subatomic particles spins. They're complex spins that are going on, and therefore orienting all of the subatomic spins in a craft would, along its spin and along its axes and its plane, would be able to travel without the effects of inertial mass, which explains how these flying saucers can do 90-degree turns at 10,000 miles an hour along their spin, or along their plane. You've never seen a flying saucer, and you guys can correct me if I'm wrong, do a barrel roll similar to what an F-16 can do. Never seen that happen. They do change their orientation, but they do it very slowly, and they shoot off at a crazy speed along the axis of the craft, which fits in perfectly with this theory, because you can move along its axis with no inertial drag, and you can move along its plane with no inertial drag, but you can't change that orientation. So if you want to go in that direction and you're facing this way, you have to first change the 5 tons that the craft weighs, and do that using some other form of propulsion. So this is not a method of propulsion, but it really is the key to anti-gravity because you're able to make a craft weightless. So we started working on it, picked up a whole bunch of equipment that I found online. Some of the stuff has, you know, serial number 10, you know, it's like the 10th one ever made. That down here in the bottom right corner is our signal generator. Goes from 9 to 9.5 gigahertz. That's the amplifier that I had to fix. Came from eBay. It was broken. This is a signal analyzer. It's the power supply for the electromagnet, and this is an oscilloscope that's hooked up to our SIGGEN to read how long the pulses are. This reads the output coming from a antenna over here, and this setup. We eventually had to cover that with aluminum to protect it from the microwave radiation that was coming out because it was affecting the scale measurement. That's something I will show you in the next video. In this video, we achieved, it was about 17.8% weight loss. You can see me wearing these glasses over here to protect me from the microwave radiation. In this orientation, there was a little bit of a headache, but not as bad. In future ones, we got much worse, so we decided to throw everything inside the Faraday cage. Okay, let me see if I can play it. Oh no, it's the next picture. Okay, here we go. 892. You can see the weight over here changing. There was a noise floor. Oh, that's about a minute. Yeah. You can see on the scope we're maintaining it. Now we're turning on the, that's basically a shutoff valve. Okay, so we did see some effect there. It wasn't that high above the noise, so I wasn't super excited with these results. But we want to move forward. We want to get better results. According to David Alzofon, Frederic's son, who wrote a book on this subject, they achieved 80% weight loss when they replicated this experiment in 1994. So those are the kind of results that I really wanted to see. And we later realized that there was a lot of problems with that inertial setup. First of all, the aluminum that I was using was not of the right purity. So we got this aluminum slugs. These are 99.99999% pure. Got the smelter oven, got the iron powder. We're going to make samples out of it. And then we later learned that because of the surface penetration of microwaves into aluminum, it's probably better to do it as a powder and encapsulate it in epoxy, which is what David recommended. So we are going to try both. And this is something that when Jeremiah came by, we set up all these samples. Jeremiah, are you there?
Yep, I'm here.
Yeah, remember this?
Oh yeah, that was a lot of fun, man. So many samples in one night. Just kept on mixing, kept on vacuuming. We really put that new vacuum chamber through its paces that night.
All right.
And so many different mixtures. Do you have the sample sheet paperwork?
Yeah, I'm going to get to that in a second. This was one of our first ones, and we were trying to get the epoxy ratio right. And also, I think I heated that up first, which was a mistake. That's why it came out kind of rough. But you see in the later ones, we sort of perfected our system. We got that nice glossy shine and degassed it properly. Again, learning on the fly, it's kind of what it is. We have all the different numbers. You can see number 1 is all screwed up. I think number 5 is the one we mostly used for this experiment. And that is the aluminum iron mix. And here is its weight. So we're using a 1.936 gram sample. Here's all the mixtures. We had all these different materials: aluminum, iron, niobium, bismuth trioxide, vanadium, it's missing an A, copper, nickel, silver, and tin, and magnesium. So we did lots of different mixtures. This is the sample holder that that I designed on SketchUp and 3D printed. And basically the sample goes in over here. These two glue together on either side of it. That's to support the top, and that holds a string. So basically it's being held in by a string that goes this way, a string that goes that way, and that's what it slides up and down on. And because of the shape of the chamber, I'm able to change the samples pretty easily because they're all about the same size. And here was the test setup that we set up. Here is the other end. This was actually the first iteration of that sample holder. I didn't show you the STL for it, but this one didn't work. It was a little over complex. I had 4 strings, really all you needed was 2. Okay, oh yeah, here is the better version. And we changed this out later for blocks of lead, basically pounded out some lead fishing weights so that they wouldn't touch each other, because this is kind of gooey and can make contact high friction. Okay, Jeremiah wasn't too happy with our current scale setup. He didn't like how jittery it was and wanted to just move to this. So we set up with the first experiment using this setup, which is basically one of these Chinese scales that he was more familiar with. There was a bit of noise involved with this as well.
The scale has a lot more resolution than the hanging scale, than the Werner scale, and it has about 15 times less instability in terms of, that Werner scale was jumping up and down by more than a gram, and realistically we're looking for tiny numbers, so that just, it wasn't any good. This scale isn't any good either, but it was better than what we had, and we're definitely upgrading our scale setup.
Yeah, we better upgrade our scale setup. If anyone knows how to, a good place to get a accurate scale with a, with the right software, we're all ears, because Vernier is the only one we can find. And if you know anything, please put it in the comments. We'll look at it later. But if anyone knows a hanging scale system, like a torsion, that pulls on, that can give you really low weights and good resolution, that's what we need.
Yeah, something with at least 0.01 grams of resolution would be nice and also have recent stability. And the other tough thing to find about scales is having a scale that's fast, having a scale that samples maybe 20 to 50 times a second at the minimum compared to these, which usually sample about twice a second. If the sample were to actually get really, really hot, as Alzofon claims, in about 1 second of actually running the machine, our scales are barely capable of even noticing that before it would overheat. So we do need to upgrade, and we are looking for help with that.
Okay, yeah, that's a good thing we brought that up. Okay, now when we moved it into the Faraday cage after we were all getting headaches, we also added on some more copper to the electromagnet. We shaved off the heads of the electromagnet, try to make the field as homogeneous as possible. It was really a backyard build of a NMR machine, and the electromagnet is really hard to work with to get that laminar field, the homogeneous field. But adding the copper reduced the power output necessary, so we were down to like 17 watts over there. There was, I'm not gonna lie, there was at one point where we were about to crack out the champagne, but then we ran some more null tests, and we found more and more problems with the when it was in the Faraday cage, especially because the RF is bouncing all over the place. It was coming back into the scale, and the scale works off of piezoelectric. So if you add a little bit of voltage through microwave modulation, you're going to screw with that piezoelectric pretty bad. So here we are inside the Faraday cage, getting rid of that problem one step at a time. The next thing we got to do is replace this little blue cable with a thick grounding shield for the next time we try it, if we can't find another scale by then. We upgraded our torsion beam as well. This one is made out of balsa wood, and you can't really see it here, but there is a brass rod that goes into washers. It's a little overkill, in my opinion, and the scale and the system is accurate enough to tell when a truck is driving by. So we plan to do all these experiments at night when there's nobody driving by. Okay, this is a thermal picture of the setup after it was ran for a little bit. The sample did get a little warm, 40 degrees centigrade. That's about 101 Fahrenheit. So it's definitely warmer than when we put it in there. And you can see the coils warmed up a bit. Although the coils were running for a while, we had so much copper on them, they're only running at around 17 watts. And that's divided by 2. So we're talking about like 8 watts per coil. And that's a ton of copper there. So it took quite a while to warm up. Next slide. Okay, so this is just an overview of the experiment. I'm going to show you this. It's just a couple minutes. This is me and Jeremiah talking when we finished our last run together. This was, I think this was back in September.
Welcome to Falcon Space. Today is September 21st, the fall equinox, and there hasn't been an update from the lab in a while. Just wanted to show you what we have going on with our latest experiment. Right now, we are working on the Alzofon experiment, which is based on the paper from Frederic Alzofon, published in 1981, Anti-Gravity with Present Technology, Implementation and Theoretical Foundation. The theory and experiment are laid out over here. Basically, you have a sample of aluminum iron inside of a laminar magnetic field. There needs to be a pulsing of a microwave source on the sample, as well as an FM detector, and all these other items. Let me show you exactly what we have going on here. There also needs to be a scale that holds the samples to see if there is any weight loss. So first off, this is our equipment. Over here we have a little spy camera, which is just powering up right now. It's gonna connect in a moment. That shows us the sample and the RF receiver. This is our signal analyzer, which hooks up directly to that RF receiver. It goes up to 22 gigahertz. Our signal generator is down over here. This is from FMI. It's, I think it's serial number 10. It was the 10th one ever made. It goes from 9 to 9.5 gigahertz, and it runs off of a simple vacuum tube inside. And it's all mechanical inside. So the numbers on the frequency gauge, we found they're pretty inaccurate. We're relying on the numbers coming out of our signal analyzer for a more accurate reading. This goes into a traveling wave tube amplifier, which we actually had to modify. It was broken when we received it. We fixed it up and now it's working. This over here is my laptop. It's hooked up to a scale that's inside the Faraday cage, which is on the other side of this wall. For the power supply, this is another thing we had to modify. Jeremiah over here is holding the camera, actually took it apart. We had to modify the different, oh, you show exactly what you did inside.
Yeah, basically, we just swapped out the front pots. So this thing had a 10 or a, what is it, 10-turn pot, 7-turn pot? It's some weird ratio potentiometer. There's the piece right there. It had a fine voltage adjustment, but absolutely nothing for the current adjustment except for this really cheapy little 5K here. And we swapped it out, replaced the two because they were a 5-volt reference rail. So we got a lot more precision on the current range, and we also put a biasing resistor in there, so we got a bit more precision exactly where we needed it.
Right, and this resistor over here, the shunt that we added to the circuit, gives us a much more accurate reading on exactly what's going on. We have to chop it away to give us a higher resistance reading, and as we power up the power supply for the electromagnet, you can see we're reading here 34.2 millivolts on the shunt. That gives us a much more accurate reading as to what is going on that electromagnet. Now,
yeah, so in this case, we when we chop the shunt, the current doesn't matter all that much. We just need to make sure that it's extremely stable. So we calibrated against another Fluke multimeter. It is 50 millivolts at 10 amps and simply sliced away until we got to that point. It's pretty thermally stable. So if you're wondering why the weird shunt, we're just monitoring the current of the output from the power supply to make sure that it does not drift around, because it needs to be really stable or the results won't be verifiable.
Another important thing that we have going on here, of course, is the Gauss meter. Now, we did have this Gauss meter, which is a Chinese variant. It's the TD8620. Unfortunately, right when we were ready to test our electromagnet, we found that the Hall effect sensor was actually broken. It got damaged from basically getting destroyed by metal. The I think parts of the electromagnet fell on it while we were transporting it, and even with our attempts to repair it, it didn't work. So we picked up this one over here. This is actually an analog Gauss meter that we got from a company here in New Jersey, MPS, Magnetic Products and Services. It's an analog one. It has, 8 different stages of Gauss readings. And we're having trouble with this one as well, because on the 3000 set, it'll max out, but on the 10,000, it'll show us 3,300 Gauss. We need much more accurate readings than that in order to run the experiment, although it does have a very nice Hall effect sensor, which is like encapsulated inside the probe, and it's very nicely grounded. It just doesn't work for our application. So we're gonna have to return this one. We got another one, and this is also a Chinese variant. It's the WT10A Tesla meter. This one's giving us very stable readings. Doesn't have the resolution of the TD8620, but it is giving us a stable reading, and it does not agree with the MPS Gauss meter. So we have some concern as to the accuracy of our Gauss readings, and the accuracy of the Gauss readings is critical for this experiment because it's 28.025 gigahertz per Tesla. We have to be in a very small Gauss range in order to run this experiment accurately. Again, here before we go around to the other side, here is the spy cam view on the sample. You can see the sample is hanging on these strings. These strings are just guide strings that are being held in place by lead weights, and that keeps the sample steady even with the magnetic field turned on. Now we're going to come around to the other side, and we're going to show you the Faraday cage. You can see over here, there's tubes. These PVC pipes go directly inside the Faraday cage. This is for the RF input. This is for the spy cam. This is for the USB. This over here is for the power for the electromagnet, and this is for the signal analyzer, seeing what's going on. So we're going to come around to the other side, and we'll show you the Faraday cage. Right over here is the Faraday cage. It's a bi-layer Faraday cage. Basically, it has capacitive conduction on the entire surface. These are just 2 separate layers, an inner layer and an outer layer. They are connected by little capacitors that are placed every square foot of the Faraday cage. And if you come inside, we'll be able to show you exactly the test setup as we have it set up right now. Okay, so first and foremost, we've had a lot of problems dealing with the scale measurement, because the scale does use a piezoelectric, I believe, and the RF does interfere with it. So we had to ground the hell out of this thing. Like, there is several layers of grounding that went into protecting our scale measurements. We used very thick aluminum foil. There's 3 or 4 different separate layers, as well as this sheet over here, a bilayer that goes directly in between where the RF is coming out and the scale measurement. Over here we have the electromagnet, or as Jeremy likes to call it, the EPR NMR laminar spintronic alignment rig. It's basically a massive electromagnet. Right down there is the sample. We currently have it set up with a bismuth iron setup. This over here is the Yagi antenna that we're using to receive the signal. There's a massive capacitor over here that cleans out the output or the load for the power supply. Let me check that out. That's a nice 2200 millifarads.
Yeah, 220,000 microfarads at 15 volts DC. So this coil is only running about 7 to 8 volts in this experiment, so it's well within range. Plenty of stabilization for the length of wires that we have for this coil.
Right, and also the entire experiment, the entire electromagnet's only using about 100 watts, so heat is not really an issue. We have seen that in the past when we had less copper on it. It was running around 300 to 400 watts, and that became an issue. I saw over time the sample started losing weight magically, just over time. we eventually figured out that it was just the heat rising and, you know, hitting the scale and whatnot. One place we're having lots of issues with is the horns. We have several different horns that we have over here. This one is an FMI. This was donated by Scott, who's a guy I met at AlienCon. It's the FMI standard gain horn. It's for this frequency range. This one is a miniature horn that we tried as well. I think I got better results on this per the signal analyzer. And the latest horn that we tried was a custom horn that I built. It's basically, we're trying to amplify the magnetic component as strong as possible. So we went with this design. It basically takes the output of the attenuator and just amplifies only, or attenuates only one side, and the other side is remains constant. We're not sure exactly what kind of horn antenna we actually want. Now, as for the signal input, it comes in over here. The antenna is in there. It's about 0.5 centimeter long. It goes into an isolator and then into an attenuator. We're not really trying to attenuate any signal over here, but it's very important we have this attenuator in place because the isolator does not like magnetic fields. It even has warning stickers on it. This is made out of aluminum or something like that. It's non-ferrous material.
Yeah, it's stainless screws. It's an aluminum chassis. And so basically we're just using the attenuator in this place with no attenuation set at all to isolate the isolator from the field of the electromagnet. That's the only reason why it's really in the beam path at all. It's basically acting as a waveguide.
Yeah, it's pretty much just a waveguide over here. Down over here, you can see this is the spy cam that we have going on the sample. It has its own little light, which is pretty useful, so you can see what's going on while we're doing the experiment. And you can also show them the scale measurement, how exactly we're taking the scale. There is a lever arm over here on top.
So I'll zoom in here and give this string a pull. Let's get the whole thing. So you can see this little thread on the top. I'm pulling up on it now so you can see how that sample moves. It moves pretty freely. The way we're doing our null measurements is just simply by cycling it up and down a few times and letting it come back to rest, making sure that it zeroes properly and that it's not sticking. We can also adjust the height. It has to really be in the exact center between the top and the bottom motion there in order to not be pulled to one side or the other when the electromagnet turns on. And we can verify that when we turn the magnet on at full power and verify that the readings on the scale do not change. So that thread comes up, it goes up to the end of the lever arm. There's the thread that goes up into the scale measurement, up through the shielding, and there is a USB-based scale there. And inside here, there's a brass rod attached to our pieces of wood, and we have some ball bearings in the end just to kind of reduce friction. The amount of torque that is in place from any amount of motion at the end of this lever arm will pretty much supersede any frictional losses that we have on those bearings anyways. But in this case, we've gotten pretty reliable measurements out of it, and it's consistent now, which is really important.
Yeah, consistency is very important. We have finally eliminated the noise problem with several different grounding wires that are going into both the walls and the floor. This floor is connected to an 8-foot rod that's in the center of the room, and there's wires that spread out that connect to everything. For the outer shield, it goes to a separate grounding rod that's only 4 feet. So there's 2 separate grounding rods that are all the way in the ground, creating a perfect Faraday cage. If we close the door over here, we will lose all Wi-Fi signaling and
cell communications,
everything.
Even the USB cable was coated all the way up straight through the wall, and then it's covered, of course, with a plate and coated up through the channel. So we really did try to shield out any possible noise contributions as a result of the microwaves bouncing around inside this chamber.
So please leave us a comment. Let us know what you think of the experimental setup. If you are an expert in RF horns, we would like to have your data on how we can best try this experiment and get the best results possible. You know, even if it's a negative, so be it. We just want to know the truth and what exactly works with Alzofon over here. And as you can see from our signage, Falcon Space is all about advancing anti-gravity technology. Even if we get a null result, that still is advancing anti-gravity technology, and we need to publish it and show everyone this doesn't work, and this is what we tried. Thank you guys, and peace out.
Okay, so that is what's going on with the Alzofon experiment. here is the next iteration of it. We got, Jeremy actually picked up a large power supply, a 5,000 volt half an amp power supply that he found at a Craigslist lab auction. There was astrophysics equipment going on over there, and there was also some waveguides that were tuned to a very precise frequency. He picked it all up and brought it down to the lab at almost less than scrap value, I think. And that power supply we were using to power a klystron, which is a high power microwave system that is going into these 3 cross guides, which are connected to a set of 3 power meters, which act as our forward and aft meter reading. Again, I'm doing most of this on the fly. We're trying to figure out how to actually work with microwaves. We've had a lot of trouble finding anyone who actually knows a lot about this stuff. And the book that I got on waveguides is not very helpful. It's just full of math and I can really not understand much of it. Here is the isolators. We got some isolators that work in this frequency range of 6.2 gigahertz. So this is in the C band. And at the end is a little antenna, and that we were using to just check out all this equipment and make sure the forward and aft sensor works. Okay. Now we needed a new electromagnet, so we just purchased this. It's a large used electromagnet that we were able to find online. I tried getting one from brand new, but the brand new people were asking for a ton of money and they just weren't answering their emails even, and we need something as soon as possible. I'm not interested in waiting half a year for it. This equipment is pretty hard to come by and there was only one available online. So we picked it up. It seems like it should be able to do the trick. We're gonna have to wait on building the waveguides, which Tanya actually helped us, gave some cool suggestions, and we're going to wait until this arrives to make sure that we can build the waveguide that would fit in between the 2 focusers over here. This seems to be some sort of, it's a plastic device that I think is designed to help change the field's homogeny, so you're able to like push it out and pull it in a little bit and tune it properly. So it's important that we get a proper Gauss meter to go with this, that with a probe that will fit in there so we can make sure that everything is correct. It is water cooled as well, so we're gonna have to probably replace all of those pipes as well. And when it arrives, we'll be ready to go on to the next stage of the Alzofon experiment. So there is another version of the Alzofon experiment. This is item number 2. And I promise all the experiments from here on in will go a lot faster than this. This was just the main thing that we're working on that we're super excited about. So this is the ARV that Paul brought up earlier. I found this picture online where it had the descriptions of the aluminum flywheel, the electromagnet coil, and the parallel plate capacitors. I've not been able to find the picture again, which is why I'm showing you a picture of a printed picture. So this picture has been scrubbed from the internet. But basically, it has an aluminum flywheel around an electromagnetic coil with these capacitors in the base. And David Alzofon told me that he showed it to his dad. And his dad said, oh, that's another way to make a dynamic nuclear orientation, for this craft without the use of microwaves. So you're replacing the microwaves by just spinning the aluminum flywheel, because the microwaves are there just to energize the spins of the valence electrons. So you can do the same thing by just spinning an aluminum flywheel inside of a coil or a magnetic field. Now, he also said the parallel plate capacitors in the base are there to pulse the electromagnetic coil. So that would be a sinusoidal wave form, because you have capacitor going into a coil, which would basically just go up and down, back and forth. And this is an experiment that we are trying. We call this EZ-Alzofon because it's a lot easier than the microwave version of this experiment. And the pulses of the electromagnetic coil, the frequency of the pulses would replace the pulses of the microwave. The microwaves are supposed to be pulsed at 5 milliseconds, which is around 400 hertz, I believe, which is in the audible range. So if these devices are using such technology, and there is a coupling between the pulse and the atmosphere around it, you may hear a hum at around 400 hertz, plus or minus. Actually, I think I got that wrong. I think it's 200 hertz. Yes. You'd hear around a pulse around 200 hertz, depending on the pulses that the craft is putting out. This is a experiment that we set up in a previous APEC conference. We did this live. We were looking to see if there's any weight gain or weight loss on this plastic piece of Teflon over here, which I used in previous experiments. Here I'm holding in my hand actually. Weighs around a pound, or maybe a little more than a pound. But the theory of dynamic nuclear orientation states that it should be contagious. So instead of weighing a spinning disk, which is kind of difficult and hard to get a proper reading on that, let's just weigh something that's nearby. And we haven't seen much. This was with a direct current going through the coil. So we couldn't really use those results for much. So we then tried it with the with a pulsed system, and here you have the setup. Basically, it's this bank of Maxwell capacitors with a spark gap over there, and to keep the system powered, we had this 125,000 volt power supply, DC, putting energy into the capacitor via a row of resistors, and then some vacuum tubes, or basically diode vacuum tubes, one-way valves for electricity. And here is what happened. And oops, I got to push play on that. Let's go. Let me show you what's going on. This is without the disc. We were just running the capacity of the coil.
I see it. I see the sparking there. You should separate those two gaps. I guess they're crossing each other. I would switch over to the superconductor coil.
Here's the superconductor coil. You can't really see it well from this angle, but there is sparks going on inside that coil. Pretty significant sparks. In fact, I think there's one picture frame where you can see. Oh, there you saw it. You're able to flying out, and they're going past all this wood to get to there. So it was really making pretty large sparks, and that is because of the high voltage, going through the coil and breaking down the enamel that was around that wire. And this gets back to, why was the electromagnetic coil encapsulated inside of glass? Well, it's because it really was being pulsed by very high voltages. And in that case, it was only 15,000 volts. And there was breakdown. So we need to make a new coil. In a talk with Todd DeCiato, who's also on our team, he theorized, if you made the coil larger on one side, it should produce a force according to his variation of the Alzofon theory. There's several variations, get that into that later. But that's exactly what you see here. Look, it's at an angle, about a 35-degree angle. And so that is the next thing that we did. Jeremy came down here to the lab and helped me build this. It was actually Jeremy and Travis. It was an all hands on deck project. We separated the different layers of the coil with fiberglass, and we're going to cover this entire thing in epoxy inside of a vacuum chamber, which we purchased special for this to fit the entire coil in it. And I still need to, this is actually going to be a pretty large job. So we need some extra hands down here before we can pour the epoxy on that and set that up. That is the next iteration of this experiment that we plan on working towards.